4.2b notes. What derivatives tell us? So in the last lesson, we learned about relative maxes, relative mins, increasing functions, decreasing functions, and just those topics. Well, this section, the derivative is going to tell us more. So we're not going to formally define these, but you're going to get a picture. What is concavity and what is inflection points? So concavity, think of a cave. See this cave? Which way is this cave pointing? It's pointing up. This whole graph is concave is facing up. So I think you see the pattern. See this cave? It's facing which way? Down. So this will be concave down. Okay. What about this one? I don't see it. Is that cave up, cave down? Is that cave up, cave down? It's actually two. So if you look at this pattern, that's a cave down pattern, right? So the region on the left, I'll do this part. I don't know what I'm doing. This part on the left, you can see, is concave down. Right? But if you look at the right side, look. If you look at it, it looks like an up, concave up, right? It's a portion of the concave up. So that section is concave up. And when something changes from concave up to concave down, the point at which it changes is known as an inflection point. I need to get the fatter pen here. That's an inflection point where a graph changes from concave up to concave down or vice versa. So this next graph here, go ahead and pause the video and see if you can figure where is concave up and where is concave down and where are the inflection points. Actually, you could do the next three. Go ahead and pause and then come back and see what the answer is. Okay, so this one, look, this is clearly concave down in this region, right? So we'll label that section concave down, right? That looks right. So I'm going to do concave down for shorthand because I don't want to keep writing that. And then look, this part, doesn't it look caved up? Because if you continue, that's concave up, right? So I'm going to do concave up for that region. Therefore, making this point the inflection point, and for just to save some time, I'm just going to put IP. All right, what about this next one? Hopefully you got it. This, to me, is part of a concave up, right? It's part of that. It's part of a concave up graph. So that's concave up. And then the right side, look, that's a cave down. That's part of a big concave down. So that section we say concave down, and making this point here the inflection point. And hopefully, like I said, you're getting the feeling of these. And then this next one here, let's do this. I think you're getting the hang of it, hopefully. This section here, it's concave what? Down. Because in the big picture, we're looking at this, right? It's cave down. And what about this side over here? What is it? Again, that's cave down too. You see it? It's a concave down. So both sides are concave down. So there is no inflection point on this. Okay? Now I am going to... So in this graph, is clearly concave up. Now let's look at the slope of the derivatives. The slope of the tangent lines, which are the derivatives. Right now, it's big negative, right? As I move to the right, it gets smaller negative, smaller negative, smaller negative, smaller negative, 0, bigger, 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 bigger. So throughout this whole region, the derivative goes from a big negative value and it keeps growing to a smaller negative, 0, and then positive and bigger and bigger and bigger. I claim the derivative is increasing on this whole graph. So when something is concave up, as you move left to right, the derivative gets bigger, 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 bigger. Now let's flip this upside down. What just happened? I actually needed 2. Whoa, weird stuff. So let's look at this graph. Now watch what happens. The slope is very steep, so the derivative is big positive number. But as I move to the right, the derivative gets smaller, smaller, smaller. At the top it's 0, and now the derivative starts to become negative, bigger negative, bigger negative, bigger negative. So what we see is the derivative continues to decrease all the way through this function. Okay? So concept, when it's concave up, the derivative keeps increasing and increasing. Here, the derivative keeps decreasing and decreasing. Now let me get a new function here for you. Let's do x to the 3rd power, and then we'll do minus 4x squared. And let's look at this function. Okay? Now, where is this concave up? Where is it concave down? We will see. But here, I think you'll agree, this is concave down here, and it's concave up here. Concave down, concave up. The inflection point, I will place this dot here. So this is concave down. Now look at the slopes, or the derivatives. The derivative gets smaller, 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 0. Then it becomes bigger, 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 negative, and then, so in this whole region, the derivative keeps decreasing. So when a function's concave down, if you look at the slopes, as you move left to right, they get smaller and smaller and smaller. Now something's going to happen to this line. Watch this line. It's going to get smaller, bigger, negative, bigger, negative, bigger, negative. At some point it stops and it starts going the other direction. See how it's getting flatter? It's becoming less negative and then starts growing in positive. So where it changes, so it's flat, bigger negative, bigger negative, bigger negative, it stops and then it goes smaller negative, smaller, smaller, smaller negative, smaller negative, and then positive, big positive. So at the inflection point, the graph stops, the derivative stops decreasing and all of a sudden starts to increasing. That point where the second derivative changes there is the inflection point. So that's the concept that's going on. Let me go back to these graphs and I will give you a visual again. Hopefully I can do this. So if we look at tangent lines, big negative, smaller negative, 0, small positive, big positive. So the slopes are increasing. When a function's concave up, the slopes are increasing. Watch this. Big positive, smaller positive, smaller positive, 0, small negative, bigger negative. So as I move left to right, these slopes keep getting smaller and smaller, which means the derivative is decreasing. So the other thing to learn is when you have a function that's concave down, the derivative is going to continue to decrease. Okay? Watch this. Big positive, smaller positive, smaller positive. So the slopes or the derivatives are decreasing, concave down. But all of a sudden the slopes start to get bigger again. They're increasing. So if the slopes or the derivatives are increasing, concave up. Hopefully you're seeing this. Big positive, smaller positive, 0, small negative, big negative. So the derivatives are decreasing on the concave down region. But here, they start to get bigger. bigger, bigger. So if the derivatives are increasing, the function's concave up. So that's what's happening. We're going to connect all these together. In the last lesson we learned, if a function's increasing, what do you know? You learned its derivative is positive. Hugely important. That's got to be in your brain. If any function's increasing, its derivative is positive. And similarly, if a function is decreasing, you know its derivative is negative. Okay? Now, let your brain kind of think on this. What if f prime is increasing? If f prime is increasing, its derivative must be positive. That's what we learned. If a function, any function is increasing, its derivative is positive. Well, if f prime is increasing, its derivative, which is f double prime, will be positive. And if f prime is decreasing, if any function is decreasing, its derivative will be negative. Therefore, the derivative f prime, which is f double prime, will be negative. Hugely important. So let's tie this in with what we just talked about. Here, the derivative went from big, smaller, smaller, 0, smaller, smaller. The derivative's decreasing. Therefore, the second derivative must be negative. Therefore, on a concave down function, the second derivative is negative. Check this out. Big negative, smaller negative, 0, small positive, big positive. Here the derivatives are increasing. But we learned if any function is increasing, its derivative is positive. So if the first derivative is increasing, the second derivative must be positive. So on a concave up function, the second derivative is positive. So here is your big theorem, the big takeaway that you must know, that you must understand, that must be in your brain. If you have a second derivative positive on an interval, then the function's concave up on the interval. And if the second derivative is negative on an interval, then the function's concave down on that interval. And the point at which f double prime changes signs, so changes from positive to negative or vice versa, that point will be an inflection point. Okay? That you have to know. That needs to be stuck in your brain. That is super, uber important for this chapter. Couple of notes. Just because a second derivative is 0 doesn't mean that there's an inflection point. Okay? But if you're looking for an inflection point, it's going to occur where the second derivative is 0 or the second derivative is undefined. Okay? So this is like similar to what we just did in our last homework, right? So I'm going to make a connection here. For relative max and mins, they occurred when the first derivative is 0 or the first derivative is undefined. But for inflection points, they occur possibly where the second derivative is 0 or the second derivative is undefined. But just because we find one of these points doesn't mean it will be an inflection point, just like this did not guarantee a relative max or min. But it's where we're going to look. Those are the only possible points where it could happen. All right, you can read this note. It is basically clarifying. Just because the second derivative is 0 doesn't mean there's an inflection point at that point. And I give you an example. The fourth derivative, x to the fourth. First derivative is 4x cubed. The second derivative is 12x squared. This equals 0 at x equals 0. But there's not an inflection point at that point. I just want to point that out. All right, let's just do fun stuff. Let's just do this. So it's important that you know what the first derivative and the second derivative tells you about a function. So we're going to do these two things. What does that fact tell you and that fact tell you? I claim this tells you the function f is increasing. And this tells us f is concave up. So what is the graph going to look like? Well, here's a concave up graph. Which portion's increasing? This portion's increasing. So this is concave up and increasing. So my answer is going to look like that. Now you can try the next, whoops, that should be a D, the next 3 and see if you can get the shape, and then you just pause and then come back. All right, what does this next one tell us? This tells us F is increasing. This tells us F is concave down. Well, here's concave down. Which portion is increasing? This portion, so it's got to look like that. So my answer would be that is increasing and concave down. The next one, this means F is decreasing. This means F is concave down. What does that look like? Well, here's concave down. Which part's decreasing? This side, so it's going to look like that. So that graph will look like that. That is a concave down decreasing function. And one more. This tells us F is decreasing because the derivative is negative. And this tells us F is concave up because the second derivative is positive. Well, what does concave up look like? That. Which part's decreasing? This part. So it should look like that. And that will be my last graph. So you should know what the first derivative and second derivative tells you about the look of the graph. Okay, here we go. I'm tired and you're tired. Let's just do this. Identify intervals which the functions are concave up or concave down, then locate the inflection points. So we learned earlier that the possible inflection points or the change in concavity points are where the second derivative is 0 or does not exist. So I will take the derivative and then I will take the derivative again to get the second derivative. And I want to know when this is 0 or undefined. I will factor out a 12. And then I will factor this. But to get 3x squared, I need a 3x and an x. To get 1, I need a 1 and a 1. This gives me 1x. That gives me 3x. But my goal is to get minus 2x. So that must be a minus 3 and a plus 1. So that's how I get those numbers. So I will erase these. I've now factored this. When does this equal 0? When 3x plus 1 equals 0 and x minus 1 equals 0. X must be negative 1/3. X must be 1. These are our possible inflection point locations. So just like when we're finding relative max and mins, we make this little box and it's a number line. So we have negative infinity here. We have negative 1/3 as a possible inflection point and 1 as a possible inflection point and infinity out there. I'll pick negative 1, 0, and 2. And what tells me inflection points in concavity? The second derivative. So I'm going to plug these in. Negative 1. If I put a negative 1 here, that's negative 3 plus 1, that's negative. If I put a negative 1 there, that's negative 2, that's negative. So two negatives make a positive. So we have positive there. I'm going to plug in 0. If I put 0 there, that's positive. 0 there, that's negative. Therefore, negative. I'm going to plug a 2 here and here. 6 plus 1 is positive. 2 minus 1 is positive. A positive and positive make positive. So now I come to my conclusions. My function f is concave up where? On the interval, so everywhere from here to here, f double prime is positive, so it's concave up on the interval from negative infinity to negative 1/3, and same thing, between 1 and infinity, the second derivative is always positive, so 1 to infinity. Why? Because, and you have to give a justification, because f double prime is positive on those intervals. So these are your justifications. Now, between negative 1/3 and 1, the second derivative is always negative, so f is concave down on what interval? Negative 1/3 to 1. Why? Because f double prime is positive on the interval from negative 1/3 to 1. We're almost done. They also ask for inflection points. Inflection points occur when the second derivative changes signs. The second derivative went from positive to negative there, and from negative to positive there, so those two are inflection points. So I will say f has inflection points where at x equals negative 1/3 and 1, because how do I know they're inflection points? Because f double prime changes signs at those points. So the justification for an inflection point is changing of second derivative changing signs. The justification for concave up is a second derivative positive, and the justification for concave down is a second derivative negative. Wow, I messed that up. Good thing I reviewed that. Second derivative negative. All right. Now, to the graph on the right, the black is the original graph, f of x. The blue is the derivative, and the red is the second derivative. Okay, and we're going to look at that, and you should be able to pull some information out of all of this stuff that I'm writing down. Okay? So let's talk. Let me double check a couple things here. I think we're good. Let's look at the second derivative and what it tells us. Second derivative tells us concavity. So we're going to look at the red. So the red is positive forever here. So that means in that region, the black graph should be concave up. And we see it is. See? Concave up. Now, the second derivative, which is red graph, is negative in this region. So on that region, if the second derivative is negative, our function should be concave down. And we see it is. See? It's curved down. And then in this region, forever to the right, let me do this over. From the right, the second derivative, the red graph, is always positive. So the graph should be concave up to the right of that point. And we see it is, look, concave up. And look, at that point, there's an inflection point because the second derivative changes signs there from positive to negative. So there's an inflection point right there. That's where it changed from concave up to concave down. And the second derivative changes signs there from negative to positive. So on the original graph, there's an inflection point right there. And look, concave up, down, concave up. That all matches. More information. So the blue graph is the derivative. Look at the blue graph. It's negative all the way here. If the derivative is negative, the function should be decreasing. Look, it's going down, 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 decreasing up to that point. It matches. Here, the blue graph is positive all in this region. That means that the graph should be increasing all the way through, and it is. The black graph is always increasing all the way to the right. So these graphs tell you a lot about the look of the function. And look, right here, the derivative changes from negative to positive. That's a justification of relative min. Look, relative min. So all of these things fit together to make a lot of sense. So that's concave up, concave. All right, example 2, we're doing the same thing, trying to find regions of concave up and concave down. And we're trying to find inflection points. So let's do this. Where can we possibly find inflection points where the second derivative is 0 or undefined? So you should know the derivative is 1 over 1 minus x squared, which I can rewrite as 1 minus x squared to negative 1/2. Well, we're going to use the chain rule to find the second derivative. So it's box to negative 1/2. We bring the negative 1/2 in front. We have box. We subtract 1 from the exponent here, and we get negative 3/2 times the derivative of box, which is negative 2x, not squared, just negative 2x. The 2's cancel. The negative and negative become positive. So we have the second derivative is going to be x on top. The negative moves this to the bottom. So it's 1 minus x squared to the 3/2, which you can rewrite if you wish, square root of 1 minus x squared, and that whole thing's going to be cubed. So we get that. There is our second derivative. Well, where's the second derivative 0? When x is 0, because we set the top equals 0, and when the bottom equals 0, we will cube both sides. We'll add x squared to both sides. We square root, and we get plus or minus 1. So we have 2 points there. So we have 3 possible locations for inflection points. So we are going to make a number line. And is there a domain? Oh, it's negative 1 to 1 on this one. Oh, wow. Did you notice that? So these are the endpoints. So they're not going to be inflection points or anything. We don't need that. We only have 1 point in the middle. And that's going to be 0. Negative 1 and 1 will be there. I will do, okay, since we're doing, okay, we'll just do negative 1/2 and 1/2. And we want to know what the second derivative is in those regions. So between these 2 points, it will always be concave up or concave down, because it can only change signs at these points. Okay? So let's go ahead and plug this in. What will negative 1/2 get us? So that will be negative. The top's negative. 1/2 squared is 1/4. That's going to be positive. So negative over positive, that will get us negative. And then if I plug in 1/2, 1/2 here will be positive. 1/2 here will be 1/4. That's going to be positive down here also. So that'll be positive and positive, which gets us positive. All right, we are ready to make a statement here. We're going to say f is concave down where? Look, it's going to be from here to here because the second derivative is negative. On the interval from negative 1 to 0. Why? Because f double prime is negative on the interval from negative 1 to 0. First statement. It's going to be concave up from here to here because, look, positive. So f is concave up on the interval from 0 to 1. Why? Because f double prime is positive on the interval from negative 1 to 0. And where does it change signs? At 0, it changes from negative to positive. So we have an inflection point. F has an inflection point. I'm just going to do that at x equals 0. And you need a justification because f double prime changes signs at x equals 0. All right, let's look at the graph and make connections here. So the black graph here, that's going to be inverse sine. The blue graph, let me double check here. The red graph is going to be f prime, and the blue graph is going to be f double prime. I think, let me evaluate this. I got to see what's going on. It might be switched actually. I think it is actually switched. Let me double check. In my head. So Yeah, that's going to be correct. We got this. Okay, we're good. So let's look at f double prime. No, f prime. F prime is always positive. That means the original graph must always be increasing, right? Because if the derivative is positive, it's above the x-axis, so it's always positive. That means f must be increasing always, and it is always increasing. Okay? Now, f prime is always positive. It never changes signs, so you're not going to have any relative max or mins, and we see this doesn't have any relative max or mins. All right, let's look at f double prime. In this region from here to here, f double prime is negative. If f double prime is negative, then the function must be concave down, and it is. Look, that's concave down. See? It's concave down shaped. And the red graph from here to here is positive, so f double prime is positive, meaning f is concave up. And it is. Look, that's part of concave up. And the red graph changes from negative to positive right at 0. That gives us an inflection point at 0 because f double prime changes from negative to positive. That's what we found here. Inflection point is 0. We found concave down to the left of 0. Look, concave down, concave up to the right of 0. Yes. Everything is making sense. The last thing for this section, and then we're going to summarize. I know a lot of stuff. Hang in here. You need to just spend some time and just absorb all this. There's a second way to find relative max and relative mins. It's called the second derivative test for local extrema, which is another word for local max and min. And I will draw some pictures to help you understand this. So the second derivative must be continuous on open interval containing c, and the first derivative must be 0. That's important. So you have a continuous function, the first derivative is 0. Then if the second derivative is positive, then there's a relative max at that point. What? Excuse me, relative minimum. I'll show you why. What does it mean for the second derivative to be positive? That means f is concave up. It must look like that, right? But where is the derivative of 0? Right there at the bottom. What is that point? It's a relative minimum. So if you have a graph where the derivative is 0 and the shape is concave up, you're going to have a relative minimum. Look, right at that point there, that's the derivative is 0 and it's concave up, relative min. Makes sense. Now, if the second derivative is negative, that means you have a concave down graph, right? So your graph is like that. But the point where the derivative is 0 is a relative max. So if you have a derivative of 0 and the second derivative is negative, definitely relative maximum at that point. Now, one little caveat, if the second derivative is 0, neither positive or negative, this test is inconclusive and you need to do the first derivative test or something else. Okay? So, in summary, to use the second derivative test, you find where the derivative is 0. You can't do undefined, only 0 in this for the second derivative test. Then you test the second derivative at that point. If it's positive, you have concave up, meaning relative min. If it's negative, you have concave down, which means relative maximum. So this one's a lot easier. Let's do this. We've already found the first and second derivative for this function, so I'm just going to copy and paste that. Let's do this. Copy and paste. Same problem. So I'm going to make your life and my life easier. Copy. Paste. Oh, and it fits perfectly. So the second derivative is, well, actually we didn't do what we needed to do. Yoshida, back up, back up. Let me erase all this. We don't need this because we're doing a different test. And let me erase these. Whoa. And let me fix this. All right, we're good. We are good. All right. We have to set the first derivative equal to 0. Wow. Sorry, but we're going to have to factor out a 12. X cubed minus x squared minus x plus 1. Now, they won't make you do this on the AP test, so that's the good news. But where does this equal 0? This will actually, I'm cheating. I'm looking at the book answer to find where this equals 0. Oh, here we go. This factors to 12 x plus 1 x minus 2 squared. Again, you won't have to do this on the actual AP test to factor a trinomial like that. But you set each factor equal to 0, and you get -1, and you get 2. These are our possible relative max, relative mins using the second derivative test. So now we have to find the second derivative at -1 and the second derivative at 2. And we just need to know if it's positive or negative. So let's just find out if it's positive or negative. If you put a -1 here, that'll be -2. If you put a -1 here, that's -3 plus 1, that's -2. A negative and negative is positive. We know that's positive. Therefore, if the second derivative is positive, concave up, so that point that we found is going to be rel min at -1. Let's plug in 2. That's going to be 6 plus 1, that's positive. 2 minus 1 is positive. Positive and positive is positive. Wait a second. I think one of those was supposed to come out to be 0 or something, and so I'm a bit confused. Let me double check my work. X minus 1, 3x plus 1. Let me double check because something just doesn't seem right. Okay. So f double prime of 1. Oh, that's why I'm confused. That's actually 1 here, not a 2. That's a 1, not a 2. So this is a 1. And if you plug in 1, it's going to come out to be 0. Watch. 1 minus 1 is 0. 0 is inconclusive, so you don't know what's happening at 1. But at -1, the derivative is 0, and the second derivative is positive. So we got the second derivative is positive, concave up. We have the first derivative is 0, so that's a relative min. So f has a relative minimum at x equals -1. Why? Because f prime at -1 is 0, and f double prime at -1 is positive. Done. That's your justification. So let's look at this real quickly. We have our original function, f of x. We have the blue function, which is the derivative, and the red function, which is the second derivative. So let's look. We have 2 points where the first derivative is 0, -1 and 1. That's what we found here, -1 and 1. Now at -1, the second derivative, which is the red graph, here, at this point the red graph is way up here, it's positive. So we found it's going to be concave up. Look, it's concave up. The derivative is 0. That's a rel min. That's what we found, a rel min. But at this point, the second derivative, which is the red, is 0. And if the second derivative is 0, it's inconclusive. And you see what happens here, that's not a relative max or min. So that's that problem. So in summary, for example 4, I'm going to do this, but I'm getting tired and I don't want to do this. But let's do this. G prime of x, this is sine of x squared. It's box squared, so the derivative is 2 times box to the first times the derivative box, which is cos x. And I set that equal to 0 to find the critical points. Wow, there's going to be a lot. That occurs when sine x is 0 or cos x is 0. When is sine x 0? I need a domain on this. This is going to be crazy if I don't do domain. So I'm going to do a domain from negative pi over 2 to pi over 2, or else I am going to be very sad. We'll go negative pi to pi, but that's going to be off the graph. Yeah, I'll go negative pi to pi. So when is sine equal to 0? Well, a lot of places at 0 and plus or minus pi. When is cosine 0? Cosine 0 at pi over 2 plus or minus. So we have 4 different locations. All right, let's find the second derivative. This might be a little uglier. The second derivative, we have a product rule. So we have 2 things being multiplied, that times that. So we leave the first alone, and we take the derivative of the second, and then we take the derivative of the first and leave the second alone. So we end up with 2 cosine squared x minus 2 sine squared x. I'm okay with that. Then I find my second derivative at 0, my second derivative at pi, my second derivative at negative pi, wow, my second derivative at pi over 2, and my second derivative at negative pi over 2. Hopefully I can do this quickly for you guys. Hopefully. So put in 0. Cosine 0 is 1, so that's 2. Sine of 0 is 0, so that's 2. That's 2. It's positive. Let's plug in pi. Cosine of pi is negative 1, but it's squared, so it's positive 1. So this is 2. This is 0, so that's 2. Let's plug in minus pi. Cosine of minus pi is negative 1, but we're squared, so it's positive 1, so that's 2. So that's 2. And sine of negative pi is 0, so that's also 2. Let's plug in pi over 2. Cosine of pi over 2 is 0, so that's gone. Sine of pi over 2 is 1, so that's going to be negative 2. And then we're going to plug in minus pi over 2. Ooh, I didn't want to do that. Minus pi over 2. Cosine of minus pi over 2 is 0. Sine of minus pi over 2 is negative 1, but we square it, so it's positive 1. Positive 1 times negative 2, that's going to be negative 2. So, I am not going to write all this out, but I'll explain. All these are points where the derivative is 0. Okay? Now, the second derivative is positive, so that's rel min at 0. Let's verify that. Rel min at 0, bam, fits. Let's do pi over 2. At pi over 2, second derivative is negative, so it's concave down, so that points to rel max. There should be a rel max at pi over 2. Can we verify that? Rel max at pi over 2. Also, negative pi over 2 is concave down because the second derivative is negative. That's rel max, and we can verify rel max there. Now, if we go all the way to pi, my graph doesn't go that far, but the second derivative is positive there, so we're going to get concave up, so we're going to have rel mins, and you'll see there's rel mins out here if you graph that out. So that is the second derivative test. So we're going to summarize the first 2 sections. Here we go. If the first derivative is positive, f's increasing. If the first derivative is negative, f is decreasing. If the second derivative is positive, it's concave up. Both these are concave up because that's concave up, that's concave up. If the second derivative is negative, concave down, concave down, concave down. If second derivative changes signs, f has an inflection point. So the point where the second derivative changes signs, f has an inflection point. So if the first derivative is 0 and the second derivative is positive, so 0 tangent line, slope, second derivative positive, concave up, that's a relative min. If the first derivative is 0 and the second derivative is negative, meaning concave down, relative max. And f prime changes signs. Okay, the point where f prime changes from positive to negative, you have relative max. And the point where f prime changes from negative to positive, you have a relative min. That is a summary of all the things you have to know from the first couple sections. Bye-bye.